homework, my 8 puzzle homework, and let's just start with the interface we have here, BFS. Let's do easy, and yeah, we can see we have the start node over here, and this is the relevant information, and we end up with a goal node, and all the information is shown throughout, and the states we have down, depth. You see, this is the direction from the last movement, and at the end we have the time and space. We can also show you another one, 5 A star. Let's do medium, and then Manhattan. Yeah, same thing. We end up with a time and space, and from a start node. So that's how it runs. We can quickly do one more. Best first. We can do hard, and let's go. Same thing. Once again, we have more time and more space here. Anyways, let me show you how I implemented the 8 puzzle. For the 8 puzzle, we have the normal stuff. We have states, we have parents, we have children, we have depth, and we have these two which tell us where the position of the 0 tile is. We also have a direction, so how the node got to where it is, and we have a string version of it, and cost and max cost. The constructor initializes everything, and then we have some other methods like we have getters and setters. So this is for all the fields. We have getters and setters, and then there's also create child, which is used in the successor to create children through these two integers, which is just the position of where the blank needs to move, and so through that we create the child, we add the child into the list of children. As you can see here, we can see the add child over here, and that's how it works. And we just have a bunch of getters and setters, and we have an isGoal method as well over here, which demonstrates if it's a goal or not. And then we have a hash code as well, which we use with the hash map. We get this from the string version of the board. Anyways, so let me show you the successor function. For the successor, it's a class, and there's a method in it as well, and we get the row and column for the blank position, which is important so we know the children. And through that, based on the position of the blank, we can see whether it can move up or down or right or left. And just say we chose up, we have a state that can go up, and we create the child, and which will be added as for the to the children of that node, and then we set the direction, and then we put it to the list and return that list of children. And then let's go to BFS. BFS is the normal familiar algorithm we see, and then we have, it's a class. We have the initial node, and that's the node we'll start with. And then we have the info object, which is very important because that's where we keep the queues, the stacks, the priority queues, and just other information like the time, the space. That's the max queue size in this case, and the visited hash map. And we use this, so we create this object in all the searches, and you can see there's some methods like time, and we call this method when we want to start the time, or when we want to keep track, and that's what we do. And we can get the space through that. Let me just go back to BFS and show you. So yeah, there's the visited, if it's a goal, same old, and prints the path, which is another important one. It creates the path if it's a goal. So we have that over here, and this takes the goal node, initial node, and it traces it back, and we have it reconstructs the path, it prints it, which is what we see on this right hand side. Anyways, back to BFS. The two checks it does is here, it checks if the queue contains the child, and also up here it checks if it contains it in the visited. And then we can show you one more algorithm, A star. I have time for that. For A star, we have comparators. We have the two comparators here for both the heuristics, and we can see the get max cost over here. That's the cost. I can't show you that because it's on the uniform. We don't have time for that, but and that's the Manhattan we get from the heuristics. It's the same priority queues. We have a priority queue here, which we use with the comparator to determine whether we how the queue is ordered. And yeah, that's it. I can show you quickly the heuristics class, which has a Manhattan method, which returns the Manhattan of a certain node, the Manhattan value, and we also have this, which tells us how many tiles are in the incorrect position, and that's what's used over here when we're doing the comparisons, or when we're putting the comparator in the queues. And it's, yeah, that's the structure of it. I'm done, I guess.